So this lesson is on the principle of mathematical induction. So let's create a rule here. So notice 1 equals 1, no surprise there. 1 plus 3 is 4. What do 1 and 4 have in common? We're adding up odd numbers, so my next one will be 1 plus 3 plus 5. 1 plus 3 plus 5, 8 and 1 is 9. 1, 3, 5, 7 is 16. So notice 1, 4, 9, and 16 all are similar. They all are perfect squares. So this is implying a possible rule, and I've given you one more again. 1 plus 3 plus 5 plus 7 plus 9 is 25. So adding the first 5 odd numbers seems to give us 5 squared. Adding up the first 4 odd numbers seems to give us 16. Adding up the first 3 odd numbers seems to give us 9. So you sort of see how this process is going to work. Let's generate a rule for it. So here we go. The first n odd numbers. So notice the first odd number, 2 times 1 minus 1. Second odd number, 3, 2 times 2 minus 1. Third odd number, 2 times 3 minus 1. Fourth odd number, 2 times 4 minus 1. Nth odd number, 2 times n minus 1. So we have this rule. We want to prove it. It certainly seems to be the case by looking at our examples here. So here is our principle of mathematical induction. This is true for natural numbers or positive integers, 1, 2, 3, 4, 5. Our usual strategy is to show that it is true for 1, and then assuming it's true for k. So if the statement is true for some natural number k, it is also true for the next one, k plus 1. So you need a starting point, and then you need to show if the previous statement is true, the next statement is true. If we can prove those two things, those two conditions, step 1 and step 2, then we can prove that that statement is true for all positive integers. That is the principle of mathematical induction. So here's the thing we're trying to prove. 1 plus 3 plus 5 plus 7 plus 9 plus ... plus 2n minus 1 is n squared. That's our goal. So what can we do with that? Well, is it true for k equals 1? So the first one odd integer is just 1. How about 1 squared? Is that 1? Sure enough, it is. So that satisfies step 1. Step 1 is taken care of. Now we've got to assume that it's true for k. So if we have the first k odd integers, 1 plus 3 plus 5 plus 7 plus 9, up to 2k minus 1, that will be k squared. So assume it's true that it's true for k. So if I add up the first k odd integers, I get k squared. What if I add the next one? Is that statement also true? So is it true for the first k plus 1 odd integers? Now think about this for a minute. If it's true for the k plus 1 odd integers, the last number over here would be 2 times k plus 1 minus 1. And this would have to become k plus 1 squared. So one of the most challenging things with this is to know what you're really trying to prove. So yes, we want to show that it's true for k plus 1. That's our strategy. We are assuming it's true for k. So if I add the next odd integer, k is replaced with k plus 1. 2 times k plus 1 minus 1. Next one over is going to have to be k plus 1 squared, replacing k with k plus 1. If I can assume this first thing is true and show that the second has to be true, I have satisfied the second step of the principle of mathematical induction. Now you may argue that this is unnecessarily complicated, and I get that. If 2k minus 1 is the previous odd integer, the next odd integer would be 2k plus 1. But I just want to show you k is replaced with k plus 1. This k is replaced with k plus 1 as the last term. That's what we're trying to prove. So this is our roadmap. This is where we want to get. This is what we are assuming. All right. Assuming that this first part is true, I want to show that it's true for k plus 1. So I want to add the same thing to both sides. What is the next number that is going to go on the left? Well, replacing this k with k plus 1, it will be 2 times k plus 1 minus 1. If I do that on the left, I should do that on the right. So notice what I have here. Okay. On the left side, 2 times k plus 1 minus 1. On the right side, 2 times k plus 1 minus 1. Great. Now the question is the right-hand side k plus 1 squared, right? Replace k with k plus 1, the right side would have to be k plus 1 squared. If we do algebraic simplification, do we get that? Distributing here, left side is staying the same. I'm not changing anything on the left side. Right side, k squared is the same. 2 times k is 2k. 2 times 1 is 2 minus 1. So 2k plus 2 minus 1 there. Then where do we go? 2k plus 2 minus 1 is 2k plus 1. So we look at that right side. K squared plus 2k plus 1. Does that factor? Sure it does. K squared plus 2k plus 1 is the same as k plus 1 squared. And is that not what we were trying to prove? Wasn't that our goal? Remember, the first k plus 1 odd integers added together to give k plus 1 squared. That indeed was our strategy. That was our goal. So this proves that the sum of the first k plus 1 odd numbers is k plus 1 squared. We did step 1, showing it was true for 1. And we showed step 2, assuming it's true for k, showing it's true for k plus 1. That's the principle of mathematical induction. Let's take a look at another example. What do I have here? Or what am I saying here? I have proven 1 plus 3 plus 5 plus 7 plus 9 plus ... plus 2n minus 1 is n squared. Sum of the first n odd integers is n squared. Why? Again, because I showed it true for k equals 1, and I have proven, assuming it's true for k, it had to be true for k plus 1, that followed. Okay, here is our next question to look at. We want to use induction to prove that 1 plus 3 plus 3 squared plus 3 cubed up to 3 to the n minus 1 equals 1/2 times 3 to the n minus 1. This is the first n multiples of 3. 3 to the 0, 3 to the 1, 3 to the 2, up to 3 to the n minus 1. The first n multiples of 3 equals 1/2 times 3 to the n minus 1. 2 steps I have to prove. First, show that it's true for 1, and then show if it's true for k, it's got to be true for k plus 1. So is it true for 1? Let's think about this. The first term, the first power of 3, 3 to the 0 is 1. So therefore, n is the first one. 3 to the 1 is 3. Minus 1 is 2. 1/2 of 2, also 1. Show it's true for 1. Again, does 1 equal 1/2 of 3 to the first minus 1? Sure does. So this satisfies step 1. K equals 1. Plug 1 in here for the exponent. 1 equals 1/2, 3 to the 1 minus 1. It's true. That satisfies step 1. Now, the harder part of this typically is to say, assuming it's true for k, show that it is true for k plus 1. That's what we want to do next. All right. So how are we going to do that? If it's true for k, then it must be true for k plus 1. That's our goal. Assuming it's true for k, so the last letter here is k and becomes k minus 1. Starting from 3 to the 0 to 3 to the k minus 1, that would be k powers of 3. And then this would become 1/2 to the 3k minus 1, 3 to the k minus 1. That is what we are assuming. What do we want to prove? We want to prove that if we add one more multiple on the left side, the k becomes k plus 1 on the right side. So one more multiple on the left side, so 3 to the k minus 1. The next one would be what? 3 to the k, because they go up by 1 each time. Or you could say replace k with k plus 1, k plus 1 minus 1. 3 to the k is the next number on the left. And then on the right, I need 1/2 3 to the k plus 1 minus 1. That's what we're trying to prove. Notice there's your extra power of 3 on the left. Replace k with k plus 1 on the right. This is what we are trying to prove. Now, how are we going to do that? We are going to assume this first part and then add that 3 to the k to both sides and do some algebra to hopefully show that they're equivalent. So here's what we are assuming. This is what we're given. Again, I want to add 3 to the k to both sides. So 3 to the k on the left side, 3 to the k on the right side. But remember, eventually I want this right side to look like this, except for k is replaced with k plus 1. That's my goal. So we need to do some algebraic simplification. How about we distribute the 1/2? 1/2 times 3 to the k minus 1/2 times 1. There you go. 1/2 times 3 to the k minus 1/2 times 1 is 1/2 plus 3 to the k. Now you will notice I have 1/2 3 to the k and 1 3 to the k, which is 1 plus 1/2 3 to the k, or 3/2 3 to the k. So all I'm doing is I'm simplifying the right side. The left-hand side is staying the same. We're adding this other number on the right side. So 1/2 plus 1 is 3/2. But 3/2 is 1/2 times 3. So this is probably the trickiest part of this analysis. Because remember, I need it to look like what my goal was. What was my goal? Let's remind ourselves of our goal. 1/2, 3 to the k plus 1 minus 1. I want a 1/2 multiplier out in front. Where am I at now? I'm at 3/2. So I want a 1/2 multiplier there. So how about 1/2 times 3 is 3/2? And then 3 to the first times 3 to the k would be 3 to the k plus 1. When you have the same base, you add the exponents. So we get 1/2 times 3 to the k plus 1. So here we go. 1/2 times 3 to the k plus 1 minus 1/2. I certainly can factor the 1/2 out again. Left-hand side staying the same, nothing's changing. Factoring out this 1/2, what do I get? I get 1/2 3 to the k plus 1 minus 1. Was that my goal? The sum of the first k plus 1 powers of 3 is 1/2 3 to that k plus 1 minus 1. Indeed, that completes step 2. That's what I had to do. That was my goal. By assuming it was true for the first k, I have proven that it's true for the first k plus 1 terms. So this completes the proof since I completed step 1, showing it was true at k equals 1. And then I showed that since I assumed it was true for k, I was able to prove that it was true for k plus 1. Notice, 1/2 3 to the k plus 1 minus 1. There's our k plus 1 thing, ending with 3 to the k, so we have a total of k plus 1 elements on the left side. This is a challenging procedure, there's no doubt about it, and it's tedious. So you've got to be careful in terms of how you set this thing up. But remember, 2 processes, 2 things you have to do. Step 1, show it's true for k equals 1. Step 2, assume it's true for k, and do some algebra to show that it's got to be true for k plus 1. That'll do it.